Today we shall look at the another important form of corrosion called as crevice corrosion. It is also called as under deposit corrosion, sometimes called as waterline corrosion if you want to call it, gasket corrosion. All these different names are given for these forms of corrosion. So, crevice corrosion is a common name. So, it is called as also as under deposit. Sometimes called as gasket corrosion. Okay, and is what similar to that is called as waterline corrosion. In all these cases, there is something very common. There is a common mechanism. This particular type of corrosion problem is industrially very important. Okay, I show some examples of how the crevice corrosion can affect the performance of a component. What you have seen here is a flange joint of an heat exchanger. Okay, the heat exchanger is made up of the carbon steel. You can see this, and the carbon steel inside was cladded with a duplex stainless steel. So, it is a stainless steel, and it is a flange joint, and use a gasket here, right? Use a gasket here, and the medium of exposure in this case was seawater. Now you see the corrosion, right? The exposure is inside here. The attack is slightly inside. See, this is inside. It is not at the mouth of this joint. So, these are the typical we call gasket corrosion or crevice corrosion joint corrosion problem. You have the other kind of joint. You will see in the case of a heat exchanger, we broadly brought out this heat exchanger in one of the previous classes. Now, you have the tube and tube sheet joint, right? Tube and tube sheet joint, and this location is the tube and tube sheet joint here, just expanded. See, please look at this a mechanical joint. It is just expanded. You have a tube. Okay. Surrounding that is a tube sheet. You join them by expanding it. Just it bites actually, and there is an airline gap. Now look at this. Only the place where it is joined, there is undergoing corrosion. It's a stainless steel. It is used in the one of the high pressure heaters in a boiler operations actually, thermal power plants. These are joints. What you see here is something I call as under deposit corrosion, right. I hope you will be able to see these spots here. Okay. These are the spots. The fouling occurred. What does it mean by fouling occurred? some kind of organic film or products accumulated on the surface of this. When they accumulated, look at this, below the deposit only is more corrosion, and the surrounding area there is no corrosion at all actually. Inside you can see that inside this tube, you see there is no corrosion here. Okay. So, wherever there are deposits and below the deposits, it can cause corrosion of in this case the stainless steel. Okay. This is a common industrial problem, okay, and it can cause premature failure of the industrial component actually, it can happen. And I just want to introduce a new book, and if you people can have a look at that. This book is An Introduction to Metallic Corrosion by U.R. Evans. I think you know all, the name is very familiar to you, right? The Evans diagrams. And it is published by Edward Arnold, 1981. Great Britain is actually it's a third edition. I just introducing this book to you because you will see quite a bit of industrial illustrations, importance, not much on thermodynamics and kinetics the way other books are dealing with, but it's a nice illustration, exposures. You will see there are some typical experiments in the laboratory to simulate the various forms of corrosion. So, when you people have time, I think you can look at this book actually. I will give you some nice illustrations as given in this book to show how this crevice corrosion can occur. If you take a lead, you immerse it in potassium chloride solution, and you place a lenticular glass like this. Keep a lenticular glass like this. Of course, in the glass you do not find liquid. Okay. You allow the lead to corrode for some time, and then you remove this if you remove this glass and observe the corrosion of the lead, you will notice somewhat similar to this. Okay. Here no corrosion, taking place, and surrounding this region corrosive attack. And here onwards, all you can cases you can see the passivity. There is a corrosive attack, and also you see over this place also see thick lead dioxide is formed. This is the plane view of the lead surface. You take a cross sectional view of this, same thing, you take a cross sectional view of this. Sectional view, right? And of course, here you will see quite a bit of lead dioxide. Here it is not corroded, this is your uncorroded area. This uncorroded area, and this area all passivated area. So, it is very interesting observation, right? Where the lenticular glass touches the lead quite it touches is the contact is so good, it replaces the liquid completely. So, there is no corrosion between the liquid and the metal, so it does not corrode. But slightly away from it there is airline gap, and in the airline gap I think corrosion takes place, okay. And these are all the corroded areas. You see that. So, there is a very fine gap, and there is a very fine gap that exists between the lenticular glass and the lead. Over there is a corrosion, and the gap is quite large, there is no corrosion, and if the glass touches and replaces the potassium chloride solution completely, of course there is no corrosion, but in between this is the place where the airline gap, the corrosion takes place. So, airline gap is a critical issue in corrosion of the lead here. This one more illustration is very nice, okay. In another case, you can take a steel, and you have a drop of potassium chloride solution, right. You have a drop of potassium chloride solution with water, and to this you add what is called as peroxide indicator. Add to this. And what is a peroxide indicator? The peroxide indicator is prepared by mixing phenolphthalein with potassium ferricyanide. So, the solution consists of what? It consists of a dilute solution of potassium chloride and the peroxide indicator, and it consists of phenolphthalein and potassium ferrocyanide. The very interesting thing happened in this case, and if one watches closely, you will see that over a time period here, you will notice the blue coloration, and here this location, you will see pink coloration. Pink color, okay. So, this is a pink color here, pink, and you have a pink color. Anybody with a chemistry background, you will understand this. When you have a phenolphthalein and you have a pink color, what does it really means? The time. When do you get pink color in a solution containing phenolphthalein exist? Anyone? Yeah? Is it acidic? Is it alkaline? So, it is alkaline. So, when you have alkaline condition only you get phenolphthalein, giving rise to pink color. So, the edges, the periphery of the droplet completely, okay, if I take a plane view of that, okay, if I see this as a plane view, the droplet, you will see the blue color, and this is your pink color. Okay. The pink happens because you have hydroxides, and blue happens because you have Fe2 plus ions. If Fe2 plus ions they interact with the ferricyanide, potassium ferricyanide, you get a blue color. And you have a hydroxide, then what happens? You will get a pink color. How is that possible? How it happens? It happens because this area becomes a cathode. What happened to this area? This area becomes the anode. You take a steel, you put in sodium chloride or potassium chloride solution. The anode is where you have an oxidation. In this case, the steel will get converted into Fe2 plus and the electrons are released. The electrons are consumed by a cathodic reaction. If the water is little neutral or little alkaline, what is the cathodic reaction? The cathodic reaction is going to be, what is the cathodic reaction here? It could be oxygen plus electron to H2O giving rise to 4 OH minus. So, it becomes alkaline. Here you have the metal getting dissolved here. So, what does it mean? Here the ion is going out as Fe2 plus, the electrons are released here, they go to this place and you have a cathodic reaction here. Okay. Here you are going to have cathodic reaction. On the center you have an anodic reaction. The reason is very simple. What is involved in the cathodic reaction? What is the species involved in the cathodic reaction? Yeah? Can you? What is the species involved in the cathodic reaction? Yeah? It is oxygen present here. So, oxygen is a cathodic reaction in the peripheral or the periphery of the drop. You have more access for oxygen there. The oxygen will enter from the air and go to the periphery. And you start moving from the periphery to the center, the oxygen concentration decreases. So, most of the cathodic reaction is confined to the periphery and the anodic reaction automatically is centered around the drop. So, you find that in a droplet you have separate anode and separate cathode spatially. So, it is not a uniform corrosion anymore, it is a localized corrosion. It is essentially, this is in fact called as differential aeration corrosion. The oxygen concentration at the center and at the periphery is different. So, this leads to the other form of the corrosion called as waterline corrosion. So, concentration cells. So, the key issue here is the concentration cell. What is the cell formed? The cell formed because of the change in the oxygen partial pressure in the electrolyte. So, that is a key for the localized corrosion. This can be very well demonstrated actually, okay. It can be very well demonstrated. Let us look at the typical stainless steel which exhibits active, passive, transpassive behavior, okay. Let us take a anodic polarization curve. Like this is your a schematic of anodic polarization curve showing active, passive, transpassive transition. The ECAR for this particular system would depend upon the cathodic reaction. Assume that the steel is exposed to water, which is a neutral water. The major cathodic reaction will be what? The oxygen reduction reaction. I consider water containing large amount of dissolved oxygen, the water containing another case less amount of oxygen there. So, I am going to draw the cathodic curves. Case 1 and case 2. One case the oxygen content is more, other case oxygen content is less. Can you tell me which of the two has lower oxygen content? Yes? Case 2. How do you say that? Yeah? Right, but how do you say that? What is the basis for that? Why does it pass very readily? Why should it cross I critical? Yeah. If the oxygen content is less, what does really happen? What is related to actually? Yeah. You have oxygen less, the amount of oxidation, amount of reduction may be less. Eh? But can you be a little bit more specifically? You have seen some relation before. Yeah, so the limiting current density is a factor that talks about, right? Isn't it? You all know that limiting current density is the concentration of the bulk of the species deduces that, okay. So when the concentration of oxygen is less, the limiting current density is less, and so you will get E car of corresponding to this, and you get E car corresponding to this depending upon the oxygen content. Okay. Of course, we all know that when there is more oxygen content, more passivation takes place, all these things. Okay. So on a metal surface, coming back to the point, on a single metal surface, in one place you have more oxygen content, in another place less oxygen content. The place having less oxygen content would not be tending to passive. The one place where having high oxygen content will tend to become passive actually, because of what? Because you need a certain current density to cross the IC value, which is I critical. You need to do that. So this also was demonstrated by another nice simple experiment actually. What was done was, if you take a semi-permeable membrane, okay, it permeates for oxygen there, and take this electrolyte, suppose you take a stainless steel, take stainless steel and you close this, but what do? You bubble one side with the oxygen there, another side you bubble with nitrogen, right. So this is electrode 1, electrode 2, okay. Electrode 1 and electrode 2, take here, okay. And also you can connect this with an ammeter. You connect with the ammeter there, okay. So what will happen now? You have oxygen here, and so what do you think will happen? Will there be a potential difference between E1 and E2? Okay. So what happens if there is a potential difference and you short that? What will happen? The current will flow. So how does the current will flow here? Tell me. Current will flow from E2 to E1 or E1 to E2? The current will flow from E2 to E1, right? And so the E1 is going to act as a anode. This is going to act as a cathode. And current flows. Agreed as these things? So what do you understand from here? If in a metal, see the potential of the E equilibrium potential for the oxygen system. Okay, what is this one? E equal to E naught plus 0.059 upon 4 here, right, and the partial pressure of oxygen, okay, upon what? The partial pressure of OH minus to the power 4. Yeah, thank you. I think it must be log here. Log here, okay. So, when the oxygen partial pressure increases, the E increases, 10 to the more noble, and so it sets up what is called as concentration cell. That leads to corrosion of metals. Now, this is only one reason for crevice corrosion, only one reason for gasket corrosion, but you will see that that is not the only reason for that. Okay, you will see the environment plays a very important role. We'll talk about soon, but the major initiative comes from the concentration cell, because the concentration cells make one place anode, then other place as a cathode, and making as localized anode and localized cathodes at macroscopic level. Please look at macroscopy. Why called macroscopy? It's a gasket. They are a few millimeters apart. It's not microscopic like the microstructures. We see the situations. These are, as I told you, important problems because there are we have a rivet joints, for example, right? You join the metal with the rivets and flanges, sometimes hem joints, and these joints would have some gap. Okay, so you have rivets. Have flanges. You have in fact threaded bolts. Okay. Or deposits, The idea is you must have an airline gap. Okay. This gap is sufficient for the liquid to penetrate. But insufficient for convection. Within this gap, there is only a diffusion process. Okay, so only diffusion. Of species. So what does it mean? If the gap becomes more, suppose see these gaps are all in the range of few microns, maybe about, let's say, 4 to 10 micrometers is the crevice depth, crevice width, I would say, width of the crevice. If you are going to be a few millimeters, what happens? then the oxygen can migrate much easily through convection process. Though they do not form a cell at all due to concentration difference, because it does not exist. So, one of the requirement for crevice corrosion is there should be a gap, and that gap has to be very small, and there should be no diffusion taking place in the system. Okay. So, that is the basic requirement for a crevice corrosion. See, whatever geometry, whatever fabrication that you do, see, there are cases where people weld it, welding, right? You talk about a TIG welding. In the TIG welding, if the fusion is not very good, if there are airline cracks, the airline cracks can become a crevice corrosion. It is not necessarily you have an external joints like that, okay. So, that kind of things can lead to crevice kind of attack in very many industrial components. Suppose I have an oxide scale, I did not remove the oxide scale, I make it loose, can lead to form of crevice corrosion taking place on the metal. But nevertheless, you need to understand one important thing. For crevice corrosion to occur, the metal has to be passive. Please understand this. Why? If the metal is not passive and you visualize the situation, the crevice corrosion may not occur. Why may not occur? Oh, I have same gap, the gap is same, but it is not a passive metal like a carbon steel, let's suppose I take, and little more in acidic environment I took it and say there is no crevice corrosion. Crevice corrosion more often occurs in stainless steels, where the passivation is predominant. Why does it occur when the metal is not passivating? Yeah, see, when it doesn't passivate, increase in oxygen content will only increase the corrosion rate. A decrease in oxygen content will only decrease the corrosion rate, isn't it? Is it correct or not? In a carbon steel, where it does not passivating, when you increase oxygen content, what will happen to corrosion rate? It won't decrease, it will only increase, because the increase in oxygen content always rises the electrode potential, that is for sure, right? No matter what the metal it is, whether it is stainless steel or a steel, the E-car will always go up. But in the case of stainless steel, when the E-car goes up, there is a chance that it passivates. But in a carbon steel, when the E-car is going up, then what happens? The corrosion only will increase, it is not going to decrease at all. So, the crevice corrosion is more applicable to the passive metal. Aluminum alloys, yes, true, it has happened. Magnesium alloys, crevice corrosion can occur. Okay. So, crevice corrosion also metal has to be passive in order to form the crevice corrosion. So, we have looked at the broad contours of crevice corrosion. Let us look at the mechanism of crevice corrosion. Okay. You can broadly say that the crevice corrosion involves, one is the initiation, the two is growth, initiation of the crevice and growth of the crevice. and the initiation of crevice is not so well understood as the growth of the crevice corrosion. Now, let me try to explain to you with some schematic what are the things involved in the crevice corrosion of stainless steel's initiation process. Let's look at some thought experiments wherein I take a metal which is a stainless steel. It forms a passive film. Please notice this passive film is thin, isn't it? We have been talking about the passive film thickness in the order of angstroms, about 40 angstroms to 100 angstroms, like that. They form a passive film and it is exposed to the environment, and then you have exposed to the air. So, when a stainless steel is exposed to the air and environment, what do you expect? You will expect that to be passivated, right? It is supposed to be passivating. So, it is passivating now. If one measures the potential at say 3 locations, you measure the potential of this, okay, E, you measure the potential of this, it will be in passive range or active range. What do you normally expect? The stainless steel is nicely aerated condition of environment, will be spontaneously passivating. So, the potential will be generally in the passive range, maybe something like 3 volt, something. I am just giving some approximate number, there is nothing unique about these numbers. If I measure the pH of this, it will be neutral or slightly alkaline, maybe let us say about 7.5, 7.5, 7.5, right. So, that is the pH of the solution at location 1, location 2 and location 3, you get these things. Now, what we do over this, you keep a nice flat glass plate, okay. Let us look at what happens now, okay. Let us now take a this is stainless steel, okay. And I will just place a small glass plate over this. Okay. Air, so water. So, I measure the E value and the pH value at time t equal to 0, right. At time t equal to 0, I measure these values just after placing. So, what would happen? It will almost show the same values, right. It will show right. Now, the corrosion reaction will occur. See, when the metal is passivating, does not mean there is no corrosion, only thing the rate of corrosion is less, the anodic reaction rate is less. So, there is a corrosion. So, what will happen now? When there is a corrosion, metal get oxidized, the reducing species gets reduced, right. Like in this case, you may add oxygen present, they get reduced. The oxygen consumption over here continues, but what happens to the replenishing of this? It does not get replenished. Because of crevice, the oxygen content with the time decreases over here, whereas the oxygen content over location here and location here remains in the steady state, it does not change at all, whereas the oxygen content here decreases. So, what will happen to the potential here? The potential will drop with the time. So, at time t equal to some x value, okay. Now, what happens now here? Here this may become still 0.3 volts and this may become, let us say, minus 0.3 volts, and this is the pH may still remain the same, it may remain the same. So, what happens now in this case? Now, the potential over here drops, it goes relatively to a more negative potential and this is remain the same. So, this now tend to become an anode and this becomes now what? The cathode now. Earlier they are almost the same. So, what happens now with the next thing that can happen is, okay, is t equal to y and E would, this n will remain the same, here may become maybe a little bit more negative. Now, what happens now? Over here the ion gets, suppose I blow this area, I magnify this, what happens? Ion will go as plus 2 electrons, right, and this electron from here go to this, go over here, am I right? And here the oxygen will tend to become OH minus, here the oxygen will tend to become minus. So, it establishes a cathode here, the cathode here and the anode here. Okay. Now, what can happen? The one more thing can happen here. What is that? Fe 2 plus can combine with water, can form ferrous hydroxide and 2 plus, right. This is possible to happen. Yes. So, this place tend to become more acidic and tend to become more positive. So what happens now? It becomes acidic and also electrically what? Electrically positive, right? You have more positive charges on this location, as opposed to that the outside has relatively more negative charges, right? So what will happen to pH now? The pH, it might remain almost the same outside, it remains almost the same, or it can become, maybe it can become maybe 9, something like that, because the pH is increasing because of a cathodic reaction. Here the pH may go less, about the pH can be about 4, pH can be about 4. That becomes relatively acidic. Please notice what is happening, that it is electrically positive. So in order to neutralize this location, what will happen? The negative ions from the surrounding areas like chloride will migrate to the chloride, bulk chloride, it goes to the Crevice chloride. Okay, it goes to the Crevice chloride. So what happens now? Then H plus Cl minus can form hydrochloric acid. Agreed? Understood? So the initiation part, if I summarize the initiation, so if I summarize initiation leads to local anode and local cathode. It leads to drop in pH on the anode and say small rise in pH on the cathode. Okay. If chlorides are present, if chlorides are present, okay, they migrate to the anode, which is a crevice. Okay. Then what happens? Then it's going to be formation of acid, leads to film breakdown, etc. So there is an active dissolution of metals. So let us now take, so we have seen that the initiation process is driven by the oxygen partial pressures and then is accelerated by the presence of aggressive ions such as the chlorides. How does the growth occur? Okay, how does the growth occur? Okay, let us look at the situation where the steel. Glass plate and the passive film. And here what happens? The metal ions M, the electrons travel here, and what happens? The chlorides migrate to this place, chlorides migrate to this place, you have H plus over here, right. Now look at the situation that this place is now called as occluded cell. It is confined, is fully diffusion controlled, so no convection taking place. Okay. Now it becomes an autocatalytic process. Please notice that the anode, the anode over here and the cathode, they remain with the time. We said in the uniform corrosion, the anode and cathode will alternate. The time this will remain as anode, this becomes a cathode, and they establish a distinct potential, anodic potential and cathodic potentials. You would expect this cathode to polarize this anode so that this becomes passivation, right, isn't it? Can you see that? We saw the galvanic corrosion before, right? You have two different metals with different potentials. What happens? The galvanically shorted, the anode will tend towards the cathode and the cathode will tend towards the anode. So it can drive, it can move. In a crevice that does not happen because the resistance between the cathode and the anode would remain. It does not allow the anode to ever become a cathode. So in the crevice there is a resistance. For ionic, I am talking about ionic resistance. See, the electronic conductivity is very good in the metal, no problem, but there is an ionic resistance taking place, and so the anode and the cathode would remain on the time. Okay. So one of the conditions of the crevice corrosion is that it occurs more in the highly resistive corrosive environment. When resistance is more in the electrolyte, what happens? The anode and cathode are well separated, they do not become a single entity at all. So that is a property of the environment that will promote the crevice corrosion, as we see later. So the growth of a crevice, people have been modeling quite a bit on that actually. Okay. And because this is a very important problem for the naval applications. In fact, even the aircraft applications where the aluminum alloys will undergo crevice corrosion at the joints and all these steps. Okay. So, a lot of work has gone into understanding of crevice corrosion and modeling the crevice corrosion kinetics of metals. Okay. So, this completes our discussion related to the mechanism of crevice corrosion. Any of you have any questions, we can discuss. Okay. If it is not there, I will complete another similar interesting thing about the waterline corrosion. Okay.
Regarding inhibitors, causes a resistive
Yeah, some inhibitors may cause, but overall the inhibitors lower the corrosion rate of the metals, right.
Does the increase in the conductivity of the electrolyte cause an increase in the uniform corrosion?
Uniform corrosion will always less. When you increase the resistivity of any environment,
conductivity is increased.
yeah, when the conductivity is increased, the uniform corrosion will increase. But when the conductivity of the electrolyte is lowered, it promotes more of uniform corrosion, more of the localized corrosion than the uniform corrosion of metals.
Does inhibitor change the conductivity of the electrolyte?
Of course, there are, you see, the inhibitors does not reduce or alter the conductivity of the electrolytes generally. Okay, generally you can say, but it can, there are different mechanisms you saw before, right? We saw that it can form a film on the surface, so it covers. If there is an anodic inhibitor, you can very well go and absorb onto the anodic site and you can bring down the corrosion rate of the systems. So, inhibitors overall will bring down the in fact all forms of corrosion actually. In fact, you will see even you can bring down even pitting corrosion, crevice corrosion and erosion corrosion. Basically, but then it may not be so effective, right. It may bring down the uniform corrosion much effectively as compared to crevice corrosion, but yeah, it could reduce the crevice corrosion to a certain degree. You can do that.
In carbon steels, is it possible that crevice corrosion starts occurring because of the presence of airline gaps?
No, you're talking about the crevice corrosion with respect to carbon steel. Okay. See, the carbon steel, as it, as I could say, that if the oxygen content is quite large, okay, and you will always see that the corrosion rate is increasing only, okay, and in fact that is the reason why wherever the carbon steel is involved, you always lower the oxygen content if possible, whether it is in a boiler water treatment or any cases. Okay. So, the crevice corrosion, in fact the crevice corrosion of carbon steels never exists. If it can exist, probably it can happen in a case where you are tending to make the carbon steel passive by increasing the pH. If you look at the Pourbaix diagram, the stainless steel, the carbon steel also can passivate in the range of about 12.5 and all like that. Okay. There is possible, but in fact the problem with the carbon steel is that if you add the oxygen content a little bit more, it start a pitting actually, it does not get into that, because the breakdown of these oxide films on an iron is so easy. Okay. So, if you slightly increase the potential beyond certain values, it can break down and lead to pitting. So, carbon steels, they do not undergo any crevice corrosion, That is why whenever you have chlorides, we simply do not have any problems. Whereas when you have some fasteners, such kind of things used for marine environmental conditions, stainless steels of most of the varieties, they face what is called as the crevice corrosion problem, primarily because they pass weight and the chlorides can destroy the passive film, quite effectively. Now, as you noticed in the mechanism of initiation and growth, now the growth of the crevice would much depend upon the environment. Assume that there is no chloride present in the environment. Okay. So, the growth of the crevice is almost negligible. Okay. So, you may have a concentration cell set up and make the one place anode where the oxygen content is low, other place where the oxygen content is higher, you may have a cathode. Okay. It does happen, but the growth of the crevice is much slow. So, that means the time taken for the failure of the component would depend upon the chloride concentrations. Like if the chloride concentration of certain environments, so let's say water. Some water may have 100 ppm of chloride, and some cases you can have 1000 ppm of chlorides. Okay. You will see later that 316 may not undergo crevice corrosion in water containing 1000 ppm of chlorides, whereas the 304 stainless steel might undergo crevice corrosion in water containing 1000 ppm of chlorides, but in 100 ppm, none of them, both of them, they do not undergo crevice corrosion, even though there may be oxygen cells are formed at all, right. But to sustain this, okay, you also have to have an aggressive environment, okay, is important for that. Okay. So, yes, it's primarily driven by the oxygen partial pressures difference between two locations, but it's even more important to see what kind of environment that you deal with. That decides what the life is, and that decides also the selection of materials for given applications. As you start increasing chloride more and more, you are going to choose better and better materials to resist the crevice corrosion. So, oxygen is one part of it, but aggressiveness of the environment is equally important. Okay. Yeah. So, then we will stop the discussion for today, and we will talk about the so-called waterline corrosion. Okay. See, what does the waterline corrosion really means actually. Okay. So, we discuss in the next class. Okay. So, thank you and